So yeah, we have a joke at Google that we may be solving AI, but AV is is going to remain the frontier for a long time. So yeah, thanks for joining me. I'm Pete Warden. I'm the tech lead of the mobile and embedded Tensorflow team. And I'm kind of a last-minute addition, but I'm very excited to be here. And what I'm going to be talking about is where TensorFlow's been, where it's going, and where we're at now on ARM devices. So the first thing to know is that we really care about working well on all sorts of ARM devices. Partly that's because we have a bunch of Google applications using sort of ARM devices, both on Android and for all sorts of devices, things like Google Home. And also, as TensorFlow, we really care about enabling people kind of across the world outside of Google to use machine learning to do all sorts of interesting things. So we have a whole bunch of really fun external projects that I can talk about that are using TensorFlow on ARM. And one of my favorites actually was from a couple of years ago. A guy in San Francisco trained an image recognizer to recognize the traffic wardens, the meter maids that drive around San Francisco streets. And he put that model on a Raspberry Pi, which he put in the back window of his car, which then texted him when somebody came near his car that was recognized as a traffic warden, so he could move it before he got a ticket. I'm not sure that's an official thing that we should be promoting, but it's kind of the sort of thing that we would never have thought of ourselves, but what we think is a really interesting thing that if we can get stuff out into the world, it can actually enable a whole bunch of really interesting use cases. And these are the kind of use cases that only really exist in the edge, in the ARM ecosystem. So where are we at the moment? We have TensorFlow and TensorFlow Lite. I can talk a little bit about this sort of the history there, but we have them running on iOS, on Android devices, and on the Raspberry Pi. And the Raspberry Pi is especially exciting for us because we've managed to actually get it to the point where you can just automatically build and install these binaries on the Raspberry Pi to get the full TensorFlow running through Python, and you can just do a standard pip install. And while we don't officially support it because we don't have the continuous integration testing set up, we have had success as well doing the same pip installs on a bunch of other ARM-based Linux systems. So we've seen a lot of uptake of people actually running the full TensorFlow on these ARM devices. Like if you've got a big, meaty ARM device that they're able to run Linux on, we've hopefully given you pretty much the same experience, maybe a little bit slower, depending on the clock rate of the processor, but a very similar experience to what you get on a high-end cloud server. Now, that is when you're looking at the full gamut of what TensorFlow can do in terms of a Python interface, in terms of training, but we also have a strong need for, hey, we just want to run inference. We don't want our Android binary or iOS binary to get enormous, and we want it to run as fast as possible. And we're willing to kind of jump through a few more hoops to kind of optimize our graph after we've done the training and get to the point where you have something that's really streamlined. So for that, we actually have TensorFlow Lite, and that is a part of TensorFlow that is pretty much exclusively designed for ARM devices. It's got a whole bunch of optimizations, especially for ARM. We have the GemLoP library that we created, I think about 2 or 3 years ago now. And that is an open source library which aims to collect the very fastest implementations we can of the 8-bit matrix multiply operations that we rely on to get a lot of the speed out of sort of ARM devices and edge devices in general. There was nothing out there really offering this kind of fixed point, low precision matrix multiply that we needed, so we kicked off an open source project, and thankfully we've actually had a lot of contributions from a lot of people, including ARM, to help us speed this up. So we're putting a lot of engineering effort into making sure that we run as well as we can on ARM. For the floating point side, we're also heavy users and heavy contributors to the Eigen open source project, which is a numerical computing library which includes the bits that we're most interested in are, again, the matrix multiply. That's what we spend the bulk of our compute doing, whether we're doing convolution or fully connected layers. The really compute-intensive parts are the matrix multiply sections. So we have spent a bunch of time ourselves trying to optimize that stuff. And we're also working very closely with the Android team. Obviously we are sort of, independent of each other, but we try and collaborate and cooperate as much as we can. And they're currently using TensorFlow Lite implementations for their CPU fallback path, and you'll see a lot of similarities between the TensorFlow Lite operations that are supported and what's supported in Android NN API. So where did all this come from? So back in 2013, I really wanted to get some deep learning image recognition stuff running on my phone when I was at my startup Jetpack. So I ended up coding up some libraries to run in that day and age. That was sort of AlexNet running locally on a device. And I managed to port it over to iOS, Android, and Pi. But it was a very, very simple framework. Google acquired my startup Jetpack, and with other people on the TensorFlow team before it was launched, I started working on the mobile support, because from the very start, TensorFlow really cared about mobile. We knew that this was going to be a key use case. We knew from internal customers that people really wanted to create products that were using deep learning on mobile devices. So we knew we had to come out of the gate with mobile support. And we came out with Android support with the very initial release. And we very quickly added iOS and Raspberry Pi support in subsequent releases. And we've been very focused on ARM improvements. We've had a lot of pressure, both internally and externally, to keep working on this. People really care about it. So we've had a team that's still growing, working on improving this. So what I want to talk about, especially with the people here who are very engineering heavy, is, okay, where are we going? What are we going to be doing in the future? The number one issue that we find our customers hit is usability. They have models that they have created in TensorFlow's training framework, and they want to get them onto mobile. And it's a very hard process, especially if you want to get down to things like 8-bit. And a lot of the toughness of that problem is that you need to often make changes or have some awareness during training. Like Rob was saying, you need to get best results for quantization, you actually need to do quantization-aware training and things like that. So we're really focused on trying to make sure that we make the process as easy as possible for people so that more and more people can actually succeed in putting these machine learning applications on devices. We see a big part of that as actually creating benchmarks which function as both kind of tutorials and examples for people to follow, but also are very clear expressions of what our typical users' requirements are, both in terms of latency and, crucially, in terms of accuracy. So having benchmarks through things like MLPerf that not only give you sort of speed numbers, but also give you an estimate of the accuracy loss that you might encounter if you take particular, things like quantization. We see that as being really crucial to opening up this code and this project to a lot of collaboration. If we can just hand people benchmarks and let them work independently, we're safe in the knowledge that, hey, if they're actually passing this suite of benchmarks, then the results are going to be good enough for our users, then I'm hoping that really opens up a lot of collaboration possibilities. We want to be working much more closely with like this growing field of people who are creating sort of new technologies on new platforms for running these kind of ML models. And like I was saying, we're very, very keen to collaborate overall. We've had a great experience with the ARM compute library where we've been using some benchmarks to kind of go back and forth between our engineers and the ARM engineers working on this. And using those benchmarks, we've actually been able to sort of narrow in on something that means that the ARM compute library is showing significantly better performance than our own hand-coded code. So we're hoping to take advantage of that and integrate with the TensorFlow Lite with the ARM compute library so that we can use that. And really, we don't see our core competency as knowing all of the intricacies of particular platforms and particular processors and writing these low-level routines. That's just been something we do because we didn't have anybody else who was kind of stepping up and doing that. As the field is growing, we're super happy to work with anybody who's actually an expert on these platforms and is able to offer really better performance than we can. We're not at all bothered about using other people's code. We would love people to be sort of contributing more to TensorFlow and TensorFlow Lite, and through lower level interfaces like GemloP, we've had a pretty good track record of taking a lot of contributions from other people, and we want to see more of that happening. We do see a lot of excitement and a lot of growth happening around accelerators in general, both GPUs, custom accelerators. We're working, you may have seen the Edge TPU, which is going to be shipping on an ARM-based, connected to an ARM-based platform. We see a massive amount of growth in that area, and we want to try and work as closely as we can with people who are creating accelerators to make sure that our users have a really good experience. What we've seen with kind of the first generation of accelerators was if you were using the exact model that made it through the translation pipeline of the vendor's tools, you would get great performance. But it was very, very hard to take your own model, bring your own model in, and actually get it all the way through the tooling. So we want to do whatever we can to help people solve that tooling problem. the other thing that we're actually spending a lot of time on these days, and we're seeing a lot of demand for, is running models on microcontrollers. We are using internally microcontrollers for a bunch of things, everything ranging from kind of the OK Google keyword detection, which runs on always-on processors that are usually like DSPs or Cortex-M type processors, to things like the Pixel's background music detection, which will actually, if you have a Pixel phone, it will listen out for music, and when it detects a song, it will just display on the sort of on the lock screen the name and the artist of the song. And we think that that is just the sort of the beginning for these kind of like ambient applications of machine learning that have to run locally on device. So we're putting a lot of engineering effort into trying to help people get up and running on these Cortex, especially Cortex-M series, we see as a real sweet spot for doing this kind of low power compute. So really what I want to get out of this conference is I want to hear from the people who are at the cutting edge of this work, the engineers who are dealing with this day to day, like what your requirements are, what the best ways are for us to help and collaborate and get help from you to move this stuff forward. So I wanted to leave a few minutes now for some questions. And also, if you want to come up afterwards, I do have some TensorFlow stickers. So even if I'm not able to answer your question, at least you'll get a sticker out of it. So yeah, if you want to jump in and sort of throw some questions at me. Oh.
So you did some integration via Eigen, and obviously ARM compute, and then gives you the compute library gives you a different path through that. Is there would you make a decision either way at some point?
Yeah, so what we've found is that we're getting significantly better performance through ARM compute library than we are through our existing Eigen implementations. Part of that is because Eigen doesn't have any inherent notion of threading. Like if you want to use threading, you need to use OpenMP, and OpenMP is not very well supported on Android. So having a framework that's actually able to make really, has kind of threading support and is able to make really intelligent, parallel processing decisions built in, I feel like is a big advantage of the ARM compute library compared to sort of Eigen basically doesn't want the responsibility of kind of understanding how threads work across all of these different platforms. So the fact that the ARM compute library is able to, I think, is a big advantage. And, we're still using Eigen in, other situations for other things. So, the nice thing is that we do get the choice of sort of picking and mixing, these technologies and using the ones that make the most sense in the particular circumstances.
So I'm guessing you may have kind of answered this in the last question, but if you're running on something like a Raspberry Pi, you've got a quad-core A53, are you actually running a multi-threaded TensorFlow at the TensorFlow Lite layer, or are you leaving the threading to the lower layers?
So if you grab the current pip binary, it's using a multi-threaded Eigen implementation that I hacked up myself, and it's really unpleasant. there's a bunch of reasons. One of them is that, especially on Android, where we put a lot of our performance effort, things like the CPU governors really mess up your multi-threading strategy. You really have to know what's happening in the system to make a good choice. The best performance I found I was able to get was if I had like up to like several milliseconds of sort of busy waiting loops. Yeah, I know, everyone here is wincing. Because what would happen would be that as soon as you'd break up the matrix multiply tiles into different chunks, send each one of them to a different core, as soon as one core finished, it would get put to sleep, even though the very next layer was then going to have to spin up that same core to do further, so when we knew that there was going to be further work happening, we would actually put in busy waiting loops just to kind of like trick the CPU governor sort of implementation and things to get the performance we needed. So threading has really been one of our, one of the things where we just don't have the expertise. We kind of get there by trial and error to figure out what we should be doing to get good performance, but it's really, really hard to figure out as an outsider, whereas the ARM team has dealt with that in a lot of different circumstances. They really have some great expertise, and that's like a great example of where we're happy to have somebody else come in and sort of have solved that problem for us.
And so one follow-up, you've obviously talked a lot about Android on Pi and Android. Does the code work out of the box on Linux?
Oh yeah,
Yep.
yeah, and actually our main focus on Raspberry Pi is Raspbian.
Okay.
So yeah, we're very focused on Linux, and we have a bunch of internal users who are using Linux on Android. So yeah, we really care about that.
Yeah. Hi, I have one question. So can you share a little bit about the status of ExcelA, and especially on the ARM platforms? Yeah.
No, that's a good question, because ExcelA is like one of Google's compiler technologies. It turns TensorFlow graphs into an intermediate representation. One of the ExcelA has been largely focused on the cloud TPU. So there hasn't been a very heavy focus on running on ARM platforms. And one of the things that we have found is that a lot of the performance that you get, even when you're doing things like intermediate representations like ExcelA, actually comes from the sort of matrix multiply and the convolution primitives themselves. We have had, we expect that there may be sort of further integration with ExcelA in the future on ARM, but that's not our focus at the moment, I guess, is because we see we still see hand coding these kind of primitives to be the place where you really get performance, and the fusings and other things that you get out of compilers don't seem to make nearly as much of a dramatic difference.
Hey, I kind of work enough on governors and scheduling side to make a comment on your previous statement that you saw that the governors were kind of screwing things up for you. Have you tried using thread pools and sticking to using the same thread? Because that would generally help, because the governors do try to remember what the thread did last time. So might want to try.
No, and I would love help on that as well. Like any sort of like debugging help we have, and that's where I'm hoping that getting some of our latency benchmarks out into the world will help people point out where we're doing silly things and give people an easy way to kind of, like dig into, places where we're leaving performance on the floor. Because I'm sure that there's a lot of places where we're just not understanding the, the intricacies of what we should be doing. So that's one of the things we're really trying to do, is open up the code base, make it easier to hack on and easier to understand, so that we hopefully pull in. We've got a bunch of external contributors, but we want more.
So one of the areas where machine learning seems to be fairly promising is around scheduling. So I'm wondering if you guys have looked into machine learning algorithms to understand when to ramp up cores and keep things active for differing workloads.
Yeah, and kind of related to that, we actually have Android Auto Awesome Battery, which kind of actually looks at, uses a machine learning model, I think on Android Pie, and actually optimizes the priority of different applications, and like kind of shuts down applications in order to extend battery life. And I think there's been a significant percentage increase in battery life just from that. So I'm actually I'm really interested in seeing how those ML models can kind of make it into some of those more tricky sort of scheduling decisions. So I think that is a really promising area. It's like anywhere where you've got arbitrary rules that you're just kind of having to make up yourself, if you can get a machine learning model to learn them, then there's often a pretty big win.
So last question.
This isn't quite ARM, but there's been a lot of attention on the Mobius neural compute stick. I was kind of curious about your thoughts on running that in combination with the Raspberry Pi and TensorFlow.
No, I love the Myriad sort of Mobius compute stick. We actually have the AIY sort of series of products where if you go to a Target store in the US, you can actually get a sort of a foldable cardboard box with a Raspberry Pi and a Mobius stick in it as part of the AIY Vision Kit. And you can run a bunch of models through that. I think there, again, one of the big challenges is usability. It's currently quite hard to take an arbitrary model and run it through the conversion to get it running on the Mobius stick. And that's one of the experiences that we went through where we're like, okay, we really, really need to get usability better, and we need to collaborate more with people who are creating these, these devices to make sure that our users are able to take TensorFlow models and actually get them onto things like the Mobius stick. Because it's great having something that's really fast, but if you can't use it, it's not that helpful.
Thank you, Pete. Thank you very much.
Thanks so much.
So the next speaker is Marc Charlebois from Qualcomm. Please, Marc, welcome.